Welcome back, all of you. So, since last some 3 or 4 classes, we have been discussing about internal interaction parameters. That is one of the internal interaction parameter that is chemical shift. We understood quite a bit about chemical shifts and the causes of this chemical shift, various reasons for that, and for example, the effects which give us to shift in the peaks, like ring current effect, anisotropy effect, substitution of electronegative atom, various concepts we discussed. So I think we have taken a lot of time discussing this. Instead of dragging too much, I think it is time that we need to put an end to this because it's a huge topic. In chemical shift, you can discuss lots and lots and lots of things. I just wanted to give you the flavor of what is chemical shift and how to utilize and what is that which grounds the shift in the peaks and what are the effects on the molecule except the stereo effect and substitution effect, various things we discussed. And little bit of thing I will say today and then we'll switch over to another parameter as soon as possible. Okay. So this is another important effect. For example, electronic effect, which causes shift in the peak position. For example, in a molecule like this, substitution of C double bond O in this five-membered ring made these two peaks. Of course, there is a chemical equivalence to move to downfield. This gets de-shielded. Okay, this is because of this. And of course, we have come across molecules substituted ethylenes, and you see, this is the shift substitution of COOET in this molecule. And remember, these two peaks, of course, again chemical equivalence is there, shifted at 6.28 ppm downfield. Whereas instead of cis, make it trans. You see the peak is already moved to another little bit another 0.6 ppm down. So close to 6.83 ppm. So this is all because of electronic effect. If you study this, why it is happening, there will be additional de-shielding here because of that. Okay. So if you can see the effect of all those things about different electronic effects in a benzene ring like this, you put a C double bond over here. Now, of course, what is here, it is a different, it's not a fully aromatic system. There's no double bond here. But look at this, these four protons are completely non-equivalent. And because of that, you can see just by substitution of C double bond to a group in this, and all the four protons are, this is little bit high field, whereas this comes little bit out, especially these two are marked, which are meta for this is more downfield compared to this one. So these are the electronic effect, and this is a classic example in cis malonates. What is happening is de-shielding is not very strong because two cis groups bend the molecule out of plane in this type of molecule. See, and it resonates at high field. As a consequence, you see in this case, this proton comes at 6.83 ppm, whereas this proton comes at 6.28 ppm. So these are all some of the examples. Of course, this is not the end. We need to learn, particularly for your molecular orientation when you are looking for your system. Various other effects would be there. You have to consider various things. Of course, there is one more important factor which can affect chemical shift is Van der Waals effect. See, this is the effect of close contacts on chemical shift in these two molecules here, which is shown. For example, this proton and this proton come in close spatial proximity. Similarly, this proton and this O comes in close spatial proximity. Because of this Van der Waals effect, it gets more shielded. See, this goes up to -1 ppm. This goes up to -2.4 ppm. This proton. So these are all some effects which happens because of substitution. It is the electronic effect. As I said, in the conjugation of this C double bond, in this case, this proton you see coming at high field, close to 2.9 ppm, whereas these two protons, 4 and 6, coming very close to this. See the effect of this on this molecule. A simple molecule, symmetric here. These two protons are equivalent, and just by substitution of C double bond O in this position, made this proton come to high field, whereas 4 and 6 protons come to downfield. And the electronic effect can be seen with a carbonyl group. If a carbonyl is attached here like this, you see what is going to happen, how the protons get, this proton is more de-shielded. Of course, there's a double bond here, you can see that, whereas this proton on the other hand moves to 2.8 ppm. See the difference, how this electronic effects can drastically change the chemical shifts, especially when you are conjugated with a carbonyl group. This proton comes downfield, whereas this proton comes high field. On the other hand, same way, of course, this is a proton, it goes in with along with this proton 6, this also comes downfield. Similarly, along with 5, this proton 3 also comes high field. This is a beautiful effect you can see when you conjugate with the carbonyl group. These two carbons with a double bond 4 and 6 come downfield, and 3 and 5 come to high field. So we can keep continuing like this. There are a lot more things one can discuss, and depending upon conjugation within a heteroatom like oxygen, which is put in this, again, how the electrons are moving here, you can find out. It is, in this case, you can see that this proton gets more shielded here, whereas if you have a sulfur here, see, this comes at 5.81 ppm, whereas in this case this proton is more de-shielded than this proton. So like this you can talk a lot of things, and of course, as I said, especially in a benzene group, we discuss some of the things in the mesomeric effect with the nitrobenzene and aniline, when we discuss how the charge density, when it is located more in the ortho and para position, how those peaks get shifted. Similarly, C double bond no CH3, when it is added to the benzene ring, of course, these protons in the ortho position to this functional group and to the para position, these two get de-shielded, whereas that protons which are in the meta position gets shielded. As you can see, meta protons come high field, whereas ortho and para protons come downfield. Of course, ortho is more downfield shifted because it is close spatial proximity with this functional group, as you can see this. Okay, the same thing, of course, if you put a OCH3 group, this also we saw when we understand the mesomeric effect with ethylene. One of the example I took, same thing where the symmetry was broken, which I showed you how electron donating group and electron withdrawing group affects the chemical shift during mesomeric effect. That's what we saw. Similar example here for the benzene ring also. We discussed about the mesomeric effect with ethylene as an example. But in this case, take the aromatic protons here. When the addition of a OCH3 group in this position makes the protons in the ortho and the para position shielded, whereas metaprotons are de-shielded. Exactly what you see. Metaprotons come downfield, where ortho and para protons come high. So these are all some of the examples we are giving. Same thing when you conjugate with an heteroatom like this NH and CH3 group. Same way, another example similar to mesomeric effect. If you see how the charges, electrons are moving, you can see that this more density of electrons, charge density is more at this place and this place, that is ortho and para yet again compared to meta. As you can see, meta protons move to the downfield. Okay, whereas para and ortho protons come high field. Of course, aromatic inductive effect with fluorine, chlorine and bromine different. Electronegativity of the substitution, the spectrum drastically changes. You can see the change in the spectrum because how ortho and meta and para protons move, in same way you can work out. This is again inductive effect on the aromatic systems. Of course, one example I want to tell you, we have not discussed this, we'll discuss later. We'll come back again later when you use shift reagents as an example. Sometimes like europium salt or praseodymium, these are all some salts which we can use when the spectrum gets completely entangled. A very overcrowded spectrum will be there, which you may be finding it difficult to analyze, for example in a molecule like this. Then if you put this type of complex, which is called europium salt, of course we have a praseodymium varieties of salts which are called shift reagents. Then what happens, it goes and attacks at this place, and It distinguishes the protons based on the proximity to the functional group when it coordinates with the shift reagent. This is in a lanthanide complex. So all these effects you can utilize when we start analyzing the spectrum. Depending on the judicious choice of what you want to see, you can make use of some of these tricks. To disentangle the complexity, you can use shift reagents. More about shift reagent will come back in one of the classes later. But at the moment, I just wanted to tell because you need to understand many things. Sometimes it so happens, you synthesize the molecule and you will see that you record a spectrum in chloroform, you will get one type. You record the same spectrum in a different solvent like dimethyl sulfoxide, DMSO. You get a different spectrum. Sometimes it appears different. You may be wondering why, what is happening. These solvents sometimes influences your molecule. The solvent effect is there on the chemical shifts. Okay. What happened? Look in this molecule, CH3CH2OH, famous ethanol molecule. Now, if I take this thing in chloroform, very clearly I am going to get a peak for ethyl CH3 group, peak for CH2 group, and a peak for OH group. No doubt about it. Very clear. What happens if we take the same molecule in a different solvent, that is DMSO? See, what is happening is this SO group of DMSO starts forming a hydrogen bond with OH group. Okay, it is intermolecular between two different molecules. SO group of DMSO and OH of this starts forming a sort of hydrogen bond. And as a consequence, you will see different type of thing. What is happening here? Remember, for this and this, spectrum is same, but you will see additional effect. You must understand what we are seeing. This CH3 group remains same. Small change in the chemical shift because of the solvent. Let us not worry about it. Look at the CH2 group. CH2 group was a quartet here, 4-line pattern, which why it quartets comes in the next topic of our discussion when we come to scalar couplings. And OH was only a single peak. Now you look at it, the CH2 from downfield moved to high field, and OH, which was around 2.5, come to 4.33 ppm, moved downfield. In addition to that, this OH, which was a singlet, appears like a triplet here, whereas this was a quartet. Now you see two sets of quartets here. What does it mean? Means because of that, this hydrogen, this proton, can interact with the CH2, make this quartets into two sets of quartets that we understand in the next class about coupling interaction. Similarly, this will interact with this. Instead of one peak, it makes this as a triplet. This is the effect of solid hydrogen bonds sometimes affect the chemical shifts, and you will see all this information. Now, as a understanding another step of effect of NMR solvent, look at this molecule. This was taken in CdCl3. What is the difference between this spectrum? Same molecule, it was taken in benzene solvent. What is the meaning of that? Here, what is happening in the chloroform? Spectrum gets crowded, and sometimes chemical shift becomes so small difference, and then I'll tell you what is second order, first order. It will become more like a first order spectrum to analyze. Second order spectrum to analyze. Moment you change the solvent, there is a change in the chemical shifts. Spectrum gets better dispersed. Look at this region. Look at this region. Well, better dispersed. Similarly, look at this portion. This has completely moved about nearly 0.4 ppm away to the high field. And such things, what happens, will aid you in the analysis of the spectrum. It helps you in the analysis because the complexity gets reduced now. Understand the problem. Sometimes you don't do anything. Simply change the solvent. Okay, when you change the solvent, sometimes because of that, you can see the spectrum gets better and better in some sort, but not always. Don't think that you keep on changing the solvent to take the NMR spectrum to get a better quality spectrum like that. No, only in some examples I'm giving you. It can sometimes happen, but by and large, it won't change so drastically. But in some examples of the molecules like this, or where we saw in the previous example, where OH was there, it was performing hydrogen with the self SO group of the DMSO, so there was a change in the spectrum. Only when there is intermolecular interaction between the solvent molecule and that of your molecule of interest, sometimes you see different spectrum. The quality of the spectrum will be different. You get better dispersion and better resolution. Okay, that not always, but please remember this point. Of course, the de-shielding, how it happens in the electronic effect, we saw this, and there is no point in going further. But I want to tell you one thing. In your molecule, if you come across OH and NHS present, there was a scale which I gave you, different regions where you can see different functional groups. Remember, I showed you one table where chemical shifts, regions of interest, where each chemical shift comes from. For example, where CH3 comes, where benzene ring comes in proton. Everything has been more or less tabulated by many people, pioneers who did work in this area. They have done a lot of work and tabulated. To start with, we have an idea where to look for your peak if you have a particular group in your molecule. But when you have OH and NHS present in your molecule, there is no distinctive scale like that. I can say in the proton spectrum, CH3 peak comes between 1 to 2 ppm or 0.5 to 2 ppm. But if you ask me, where does OH peak comes in my molecule, or I have an NH proton in my molecule, where does that NH peak come? I cannot tell you offhand. There is no distinctive scale for these are called exchangeable protons. For this type of exchangeable protons, there is no preferred region of observation. It can move anywhere in the spectrum depending upon the type of interaction. Okay, this is very important and we should remember that. It also depends upon the physical condition of the experiment like temperature, solvent medium, okay, solute concentration, various things depending on the hydrogen bonds. So, but one thing is you can also notice if your molecule is forming a hydrogen bond, this leads to significant downfield shifts. You can understand if OH is there, NH is there, it is forming a hydrogen bond. That particular proton can move to downfield. Remember in the example of ethyl alcohol with when it form a hydrogen bond with the dimethyl sulfoxide, what happened to OH peak, which was somewhere around 2.5 or 3, it moved to 4.3 ppm. Remember, that is the thing. So when there is a hydrogen bonding, the peak moves to the downfield. Now you ask me a question. How do I know what type of hydrogen bond it is? If your interest is to study hydrogen bond, weak molecular interactions with the molecule, and if you want to know if the hydrogen bond is intermolecular or intramolecular, both are possible. Can we identify by NMR? Of course we can do. There is a way for it. But we will not go into that details. When we will come to that application, if there is time, we will discuss. Otherwise, simply remember, if there is hydrogen bonding in your molecule, weak molecular interactions are there, you can study by NMR because hydrogen bonded proton moves to downfield. Significant downfield shift will be there. Okay. So this is a simple example. When a molecule like this is there, when it forms a hydrogen bond with the OH, intramolecular hydrogen bond is there, then how the peak is moving OH, there is very little drift is there. Whereas in take ethyl alcohol, then what happens? It can form an intramolecular hydrogen bond with itself or with ETOH. Then what happens? As you keep on increasing the concentration of ethyl alcohol from low concentration to high, you see OH peak. It was somewhere here. It comes here. In fact, OH peak was going beyond CH3. That's what I said. Exchangeable protons, OH and NH, there is no distinctive chemical shift range. If at very low concentration of ETOH, it was beyond TMS, in very beyond CA3, that is very high field. As you keep on increasing the concentration of ETOH, see, it moves so much downfield. Drastic shift is there. So these things helps you in understanding hydrogen bonding and other things. Okay, so I have given you some basic idea about various things about chemical shifts, how it arises, how do we express in ppm, frequency, what happens as a function of magnetic field to this thing, and what are the things which contribute to the shift in the peaks, that chemical shift, why it comes, and what happens if there are different functional groups present, how do we use some idea to interpret with the electronegativity substitution there, with the ring current effect is there, if there is anisotropy of the bond is there, all those things, some basic ideas I gave. Of course, these are only the some physical pictures. Clearly, I am giving you idea to start interpretation. But mind you, if you want to understand NMR, it's a huge ocean. Lot more things you can discuss. So this should be more than sufficient to make you to begin the analysis already. Okay, and rest of the thing you have to capture yourself. You can go and read lots of fundamental books how to interpret many of these things. There are many more ways to interpret. I have taken only few examples. Lot more examples we can take, and then you will become a master of someday. With this, now I ask you one question. Okay, we know where the chemical shifts come, everything. We had some idea based on the tables which was given by the workers in the field over years. That is a starting point for analysis. But if you can ask me a question, is there any way empirically I can calculate and say I can predict where should be this chemical shift of a particular peak in my molecule? Supposing I have some small molecule, can I predict where I should look for this peak, in which region in the NMR spectrum? So empirically, there is a way to predict chemical shifts, not for all big molecules. Remember, it is just some idea. There are examples in small molecules, in both aliphatic and aromatic, both for proton chemical shifts and carbon chemical shifts also, which I tell you later when we come to heteronuclear analysis. There is a way where empirically we can predict the chemical shifts. They are called Schulleri rules. Remember, they are called Schulleri rules. See, what I am going to tell you is, so these things, if I start discussing, it will drag a lot of time. Another half an hour I require to explain to you with examples. But this is another interesting topic. Please remember, I have not covered this topic to empirically predict chemical shift by using Jim Schulleri rules. I'll try to come back if there is a time, so that we can discuss about what how with some example, what is the experimentally determined chemical shifts, or what is the theoretically calculated or empirically predicted chemical shifts. So one thing is, now the choice is I can go to the discussion of the second interaction parameter called coupling interaction, scalar coupling, or I don't know how much time I am left with this or there. What I will do is, instead of changing the topic and coming back to the Schulleri rules again, I will give one or two examples quickly, because these things is not practiced too much nowadays. Nobody uses these things. This is only an idea which was given in the early days of NMR by Jim Schulleri. Just to get a feel, I'll give you one or two simple examples in about 10 minutes instead of coming back again, so that we can go next class, we can start afresh with scalar couplings. So now the question I asked you, how do you derive the chemical shifts using Jim Schulleri rules? Remember, I was telling you the chemical shifts arise because of various reasons. Electronegativity, electronic effect, hydrogen bond, ring current, several effects are there. And in a given molecule, this is not one effect. There are multiple such effects could be there. You can simultaneously have electronegativity effect may be there. There may be hydrogen bond going on. There may be ring current effect. Many things may be possible. It is not that exclusively only one interaction is present. One type of effect is seen. But interestingly, what Jim Schuller rule says is, if you know these things, there is a way we can find out the effects of all those things, because all these effects are additive. You can add all these things, different effects, and finally get to what is the chemical shift for a particular proton. Then where do you add it? You must have something, right? And there is a base chemical shift is given for a particular group by Jim Schuller. Base chemical shift. With base chemical shift, now you look at the other groups which are present and find out their contributions, which there is an empirical way it is already predicted, and keep on adding these values and get the finally total value of this thing. Then you will know what is the total chemical shift because of addition of all these effects if they are present to the base value. And do the experiment and find out the chemical shift experimentally. And in most of the cases, by and large, they are comparable. You understand? This is the way we can predict this thing, chemical shifts. But of course, nowadays with the most advanced things are available nowadays, it is not nobody is interested in doing this type of predictions, and there are lots of ways to get the chemical shift by using Gaussian and other things. This is, but an idea is very important to understand. What I said is, for example, if you want to identify the type of protons we have, like aliphatic could be like this, olefinic, aromatic, ketone, alcohol, many things could be there. Okay, so this type of proton, if it is there, what Jim Schuller said is, there is a base value of chemical shift for all those things. Take a base value. How do you get the base value? It is already there. People have worked out, and we know what is that base value. To start, the value given to you. You don't need to worry about it. Then start summing up the various contributions one by one. Keep on adding everything and find out what is the total chemical shift you get. You get the point. And now that should be your predicted chemical shift after adding all the contribution to the base value. Now, for example, we take this group CH2, which is an R1 substitution and R2 on either side. Or we can have a CH, which is R1, R2, R3, R3 substitution. And then CH2 can have an additive effect because of R1 and R2. Need not be additive, it can be subtractive also. Additive means that all these factors are taken together, but this contribution could be negative also. Similarly, take a CH proton here. This if I have R1, R2 and R3, again for this proton all these additive groups which are close to it, and if here is something which is 25 bonds away, don't worry, because that's effect as bond increases, effect reduces. We saw inductive effect, if you go 3 to 4 bonds away, effect is less. That's what we observed in several examples of chemical shifts when we're trying to understand what happened if we lengthen the chain like that, right? So at least 1 or 2 substitutions next to each other, if you consider, we can get the chemical shift. Okay, this is a simple example. I'll give you 1 or 2 examples so that we don't have to go deep into these things, Jim Schuller rules, but we should have the idea. I am considering the example of a CH2 protons. CH2 proton, there are 2 protons here, and R1 and R2 are the substituents here on either side. Okay. If this is the type of molecule you have, if I am looking for CH2 group with a substitution on either side, then according to Schuller rule, base value for this is 1.25 ppm. That is the base value. And for this, the effect of R1 and R2 have to be added up. Then you know what is the total chemical shift for CH2 protons. Did you get my point? Don't get confused. We'll take the simple example of this group. Okay. For that, we'll take CH2Br2. Dibromoethyl. What is going to happen? He says for this type of thing, 1.25 is the base value. Take 1.25. Now, What is the effect of the substitution here? How much you have to add up? He has a table given. Remember, for different substituents, table of contribution for chemical shift is already made. It's a lot of work. We should really appreciate the quality of the work they did and how much they have contributed for our understanding. So much of work has been done and they have made a list. If there is a bromine substitution, go into this table. Oh, if there is a bromine attached for CH2, you have to add 1.9. If instead of bromine, if let us say OH is attached, then you have to add 1.5. Now take the example of CH2Br2. There are two bromines attached. Take the base value of 1.25. Now what is for each bromine it is 1.9. For two bromines, R1 and R2 on either side, 1.25 plus 1.9 plus 1.9, you add up, you get 5.05 ppm. This is the predicted value. In experiment, when they really did the experiment, they found the value to be 4.94. Yeah, but 0.1 ppm difference is there. But look at this nearness of the value of the predicted value. So this shows an idea that by and large, to some extent, you can predict the value. Don't say that I don't have to do NMR experiment now onwards. I know this value, I will predict it. No, it is not always true. This is only accurate and not accurate, approximate. But if you want to really get the chemical shifts, you have to really do the experiment to analyze. Don't go back tomorrow and say I have this table, I know what to do, and I save the experimental time. I don't have to do any NMR work. No, don't do that. That is not right. Okay, this is an important point. Now what happens if I consider a CH proton? If there is a three such substitution like this, R1, R2, R3, same way, depending upon what is the R1, you can do that. Okay, very simple way. Now I will take the example for aliphatic carbon CH3Cl. For base value for that is 0.23. That is for the chemical shift of the methane. Remember I told you, it is chemical shift of methane. Now you have to add the total value for the other substitution. Now if there is a chlorine, it is 2.53. Base value is 0.23 plus 2.53. If you add, it turns out to be 2.76. But what is experimentally observed is 3.1 ppm. Now extend this logic. We also did that. What happens if you change the substitution of number of electronegative atoms, how the chemical shifts. We saw that, shifting of the chemical shift, and we knew more the electronegative atoms, more the number, and it shifts more to the downfield. We observed that in one of the previous classes. Okay, I hope you are with me. Don't forget, we discussed this point. What is the chemical shift for CH3Cl, CH2Cl2, and CHCl3? All the three we got it. And this is the calculated. This is experimental. Now let's do the same thing for this molecule, CH2, Cl2. Base value, take it, and Cl2 is 2.53 times into 2. If you add it up, it turns out to be 5.29. And experimentally, what is observed is 5.3. Almost matching, right? Now for CHCl3, calculated value 3 times you take it and add it up to this base value, it takes 7.82, you get it, but experimentally 7.27. So all this value of prediction of the chemical shift using Gibbs-Scheele rules gives you an idea about the contribution from the different substituents. You should know the contribution from each of these substituents. If you have a table, if you know the base value, you can arrive at approximate value of the chemical shifts. You can predict it. Okay, so with this last example, I am going to stop here because there is no point in going too much about this thing. This basic idea is with a base value, you have to add the value of the substituent. That's all. Now, for aliphatic, many aliphatic compounds, again, this is taken from one of the books where you can see for different substitutions and substitution in which position. That is also important. For example, with respect to substitution, maybe in the position 1, 2, and 3. And if the substitution is different position, what is the contribution? And keep on adding for that. For example, in some cases it can be negative, you see, minus here. So it can be minus here some cases. So as I said, it's not always additive. It is only the contribution factor which we have to take into account as a sum while working out the approximate value of the chemical shift. Okay, predicting the chemical shift. Now for this molecule, example for this one, substitution effect for C2C3 is 0.244. For oxygen at C2 is 1.021. You can see oxygen 2 at position 2, 1.021. Oxygen at position 3, 0.004. See, 0.004. Take that value. CR3 at the CA3 group at position 3, you will see that minus 0.038. Add up all this value, and this is the base value for this type of molecule. And totally, if you add up everything, you get the chemical shift of 2 ppm approximately for this proton. You understand? So experimental determined value is something which is okay, 2.2 it comes, okay, around 2.2 it is there. Okay, so like that you can find out chemical shift of the alkenes for trans cis geminal coupling if it is present, what happens if it is in a cis position, geminal position, trans position. And for this case alkenes, base value is 5.28. We have to take what happens to different substitution, whether it is a cis to this proton, geminal to proton, trans. If there is a geminal group, let us say is proton, what is geminal is proton, then value for this is 0. If it is CH2N, take 0.66 is geminal, and trans, if it is let us say bromine trans, take 0.55. Like that you add up and you will know what should be the chemical shift for this proton. Like that you can easily do. This is the basic idea I wanted to tell you about Jim-Shuley rule to predict the chemical shifts. Of course, if I have to discuss this time is not enough. I need at least another half an hour to 1 hour to give more example and slowly to calculate and show what we can do and everything. Okay, and of course right now I have lots of examples to discuss, and one of the important application I tell you with the Jim-Shuley rule, in a molecule like this, I told you in ethylene molecule, depending upon the substitution you can calibrate the chemical shift. That's what I showed just now in the example here. Okay, you can find out what is the substitution and calculate. And in one of the example like this, the question was whether this is the molecule or this is the molecule. Okay, so whether COOET is cis to this or trans to this proton. Because experimental value was 8.22. Now what they did is they started making the calculations by taking this base value for 5.23, started adding all the substituent effect, and if this was the case, if it is COOET or CN group cis to this, you will get this is the chemical shift approximately predicted, whereas in this case it is 8.26, and this is very close to experiment. So these are one of the few applications of Jim-Shuley rule which used to be there in olden days. Okay, now enough for the day. I'll stop it. I have given you the basically a vast information about chemical shifts, their prediction, various ways to extract the chemical shift, as how to know what happens to different substituents and everything. And about 3 to 4 classes we have discussed about it, or even more. So that shows the vast voluminous nature of this information available about chemical shifts. So rest of the things I leave it to you. This is only the initial point. Rest you have to build up on your own. Start reading more and more. Next, tomorrow I'll come back. I'll discuss more about another interaction parameter called scalar couplings, indirect spin coupling. That's another very important parameter with which you can start analyzing more complex molecules.